Hello, welcome to the second lesson of our chapter on rational functions. Today we're going to be learning about discontinuities. Now graph these two things on your calculator. To do so, you'd need parentheses around each of them and a division sign in between. Now just graph one, take a look at its graph, and then modify the first one. Just change that 6 to a 5, and then look at the second graph. Pause the video until you have finished. Alright, so what you should have seen is that there are two different graphs. One just looks like a parabola, and the other one kind of does this funky stuff around here. Now, there are two types of discontinuities. This one is called a removable discontinuity. It's spelled right here. It's kind of fuzzy in the actual picture. And this one over here is just called a vertical asymptote. We know about asymptotes. Now, we need to discover what makes this function do this and this function go haywire right around. Now, both of them, even though your calculator looks like this is just a parabola, it actually has one space out where, because x cannot equal 3. Where x equals 3, it creates a 0 in the denominator, which is impossible. So even in your calculator, even if you can't see it, if you look in the table, at x equals 3, it will say error, because you can't have an x equals 3 in this equation. Now, as x gets closer and closer to 3, our first function, f of x, gets closer and closer to, see how this gets to 499, 5.000. This gets closer and closer to 5. So if we pick values very close to 3, f of x is going to be very close to 5. However, in g of x, if we pick a value very close to 3, it doesn't go towards 5. It goes to either positive infinity if it comes from the right, or negative infinity if it comes from the left. So our limit here is going to be positive and negative infinity. Now, how do we know when there's a removable discontinuity or vertical asymptote? Well, all we changed is this number. What will that number do? So let's use synthetic division on both and see what we find. So let's look back at this one. If we do synthetic division, 3, that's going to be 1, negative 5, 8, and negative 6. 1, 3, negative 2, negative 6, 2, and 6. That one divides out evenly. Over here, we just changed that by one number. Oops. My computer program doesn't like it when I go off the screen to the right. 1, 3, negative 2, negative 6, 2, and now this 6 will give us a remainder of 1. So if there's a remainder, it's going to create this vertical asymptote. When there's not a remainder, it's going to create a removable discontinuity. So what kind of discontinuity does this have? Well, x minus 2, let's see if I'm dividing it out the old school way. We could do that, but let's do it synthetic way. Now there's no x, so we have to plug in a 0, like so. This would be 1, 2, 2, 4. That cancels out. So this is a removable discontinuity. Now we can find this without doing our synthetic division, because we know this top is going to be x plus 2, x minus 2, over x minus 2. And these things cancel out, so that we know this is going to divide evenly into the numerator. So that means it's going to have a removable discontinuity. Now, if we look at this, this would be x plus 1, x minus 1, These are our factors. Will this divide evenly? The answer is no. If you want to check using synthetic division, 1, 0, negative 1, and you can see that we will have a remainder. So this is just a vertical asymptote. And that's going to be at x equals 2, whatever makes the denominator 0. And what about this one? Is there any two numbers that multiply to 4 that add up to 4? 2 and 2, you can't get one would have to be positive or negative. I can't think of how to factor this. So let's try the synthetic division. 1, negative 4, negative 4. Obviously this has a remainder, so this will be a vertical asymptote at x equals negative 1. Now try this one. Pause the video and see if you can do this on your own. Now I think I can factor this numerator, because this could be x minus 4, x plus 1. Since there's an x plus 1 in my numerator and denominator, this would be a removable discontinuity. Now, the value of that removable discontinuity would be at negative 1, and if I would cancel these out, this isn't necessarily equal to x minus 4, but when it would resemble the y equals x minus 4 graph, except for at negative 1. So if I put in negative 1, negative 1 minus 4 would be negative 5. So my removable discontinuity is whatever would cancel this out, so negative 1. If that gets plugged into the remaining function, that will give us our y value of our removable discontinuity. So let's try it up with this previous problem. This one, these two would cancel out. So this would go towards x plus 2. So my removable discontinuity, our x value would be 2. And if I plug that into the remaining function, 2 plus 2 would be 4. So at 2, 4, that would be where a function has its discontinuity. All right, and now we're on to the homework. Good luck.